Yeah, I was in physics class.
Yeah, you're lucky.
Some of the fire alarms don't
I was
make
laying in bed and all of a sudden it went off and I was like, oh, this is a good morning.
It doesn't even sound like a fire alarm when it goes off. It goes off and I wake up and I'm like, what's going on?
Ours is loud as...
No, what is going on? Why does she look unnecessarily nice today?
You look cute.
Why are you all dressed up, bro?
There's no particular reason.
She didn't have any more laundry.
Yeah, why can't you just dress up?
Well, so when you want to have laundry, you look like this. When I want to have laundry, I look like this.
When you don't have laundry, you take out your best clothes. Because you be like, I don't want people to know I didn't do laundry in a while.
Well, that's supposed to hurt.
You look like the Queen of England's about to come Shania you.
Shania you?
Do you feel like being shnited by the guy?
I feel like being shnited, guys. I love practice tests.
Oh, God.
I do, it's so
okay with
kind.
this.
We have an in-class test for Friday.
Dude.
For F, yes.
How do you miss these?
On that day.
The 20th Wednesday. I get to practice to actually take a test with them. I hope I get a B pause. Okay. Got class on time.
But we're still going to have the other half of the test on Monday, right?
No, plans have evolved.
Whoa, what level is it?
The next level.
Let's wait another minute. Oh, I guess it's time, isn't it? It's time enough.
Or did you use a moonstone?
Pardon?
That was good. That was
Cookie Monster.
touche.
Sorry, that one doesn't work. Let's see. So, for Wednesday, we're going to go over the homework today that you have. You're turning in now. For Wednesday, you're going to do a practice test. You're going to bring to class, and we'll go over it in class. And the test on Chapter 7 will happen on Friday, and it will be a rather specific test. It will be concentrating on Chapter 7. And the character of the test will be pretty much like this that you're going to do. Okay. Then on Monday, we're going to start Chapter 8, and that gives us, that's the last class before the Thanksgiving break, and then after Thanksgiving, we have 3 classes, and then finals week. So we'll do Chapter 8 the last week. And then on the last day of class, we'll mostly review the last couple of chapters. And then we'll have fun. Okay. So, so in addition to maybe we should just go over today's homework. And we did quite a bit of it in class. At least the Atwood machine. So you now have the solutions in hand. So do you have any questions about the Atwood machine problem, which is to do the Atwood machine with the...
This is actually about the final. Did we ever decide when we were going to be doing that?
No.
All right, I just wanted to make sure.
Yeah. We have, as I said, 2 days that we can choose between. Yes, ma'am.
What are the 2 days? Do you like them overall?
No, I don't. I don't have it with me. So, but the 2 days are determined, one, by this time slot. So there is for most of your classes, there is a final time that's determined by when the class meets during the week. And there is an alternate time, which is the common exam time for 122, Physics 1220, I guess they call it now. So, and those are 2 different times, because there are lots of sections of Physics 1220, and so all of those sections will get together to take the final at their common exam time. So we could do either one. And in the past, I've tried to kind of leave it open, but there does seem to be there's never a clear settlement of the issue, at least in the past. Some people want to wait to the end of the week, put all, because they want more time to study. Other people want to get out of here, so they want to do the exam sooner rather than later.
I think our common exam time's on Wednesday, because right now, as mine's set up, I have 3 exams on Wednesday. Oh my.
Whoa! Overachiever.
Is one of the options like
I have
that
4
Friday?
classes.
Yes, I think it's Friday. As I recall, in mine, I have a Friday. So there must be this time slot. We happen to draw a time slot. You can look it up on the registrar website. It has all the final exam times are on the registrar's website. See, so.
Friday.
Not on Friday. But I don't really remember. I mean, I shouldn't trust my memory in regards to that. So. Okay, so with regards to today's homework problems, any questions about the Atwood machine?
Well, I was looking up some of the things I had to do this. I saw a method besides the one we used that involved, instead of just direct substitution, it was like you add all the different equations together.
I didn't actually choose one of the ways, right? I don't have a solution for that. You can do it any way you like. It's a system of 3 equations and 3 unknowns, or it gets down to 3 equations and 3 unknowns. So you could do it whatever way you like, as long as it's right. And I didn't actually choose one here. I assume that you can figure that out. If you're looking for possibilities, if you get to the bottom of the second page there, and then I over r squared a is equal to T2 minus T1. If you keep it in the form where the tensions are like that, then if you add all the equations together, the tensions will drop out usually. Let's see. No, we're going to have to subtract. We're going to have to change the sign on this one. This would have to be like that. There we go. Flip the sign around on that one. Now, if you add them together, the tensions will drop out, which gets you 2 unknowns gone in one step. So this is going to be M2 minus M1G. And then the solution for A is given at the top of the 3rd page from that, to solve for A from that. So there are numerous tricks that you can use to solve 3 equations and 3 unknowns, but I expect that you can do it. Okay, so how about the question here, which was not asked in the homework? What is the weight of this device?
Pulling on the ceiling?
Yes, right. So you have it's pulling on the ceiling with some force. What is that force?
It's M1 plus M2 plus the mass of the pulley times gravity.
Okay, so that's what it is not.
It's M1 G plus A plus M2 G minus A plus the mass of the pulley.
Yeah, it's not M1G plus M2G plus the mass of the pulley G.
No, I meant
It's not equal. It is not equal to that. It's not equal to the. When they're accelerating, it is not equal to that. Right. It certainly matters. Now, if you go and were to do something to keep the pulley from turning, then this is exactly what you would get. It would be the sum of the 3 weights if the pulley is not turning. But as long as the pulley is free to turn, meaning to accelerate, then the weight, the force that's applied onto the ceiling, is not going to be equal to that. That's the surprise. And that was the same thing. We had the same thing happen when we did the massless pulley. We had the same thing. Ms. Shaven.
Is it not M1 parentheses G plus A plus M2 parentheses G minus A plus the mass of the pulley? Isn't that's the 3 tensions, or the tensions?
I think so.
Mass of pulley.
It's going to be specifically, it's going to be T1 plus T2
Yeah.
plus the mass of the pulley times G.
That's what I thought.
Right. Which you can see where T1 and T2 are obtained in the solutions. And you can see that by looking at the pulley, the force diagram on the pulley itself, there will be the weight of the pulley, and then there will be the two tensions, T1 and T2. And that pulley is in equilibrium with the fourth tension, the fourth force, which is the tension pulling up on it, which is the same force that it pulls down on the ceiling. Okay? And so you can see, because the expressions for T1 and T2 are not very simple, it's actually a fairly complicated expression for the total weight. Okay. All right, so let's see. What was the next one? The next one, I guess the next one had to do with, was it two different things spinning? There was a pulley that was spinning, and then also a sphere here, had a rope tied around it. Was this the device?
Yes.
And then a block that's hanging from that. So we have the moment of inertia of the pulley, we have the moment of inertia of this sphere. And there's also a radius for the sphere and a radius for the pulley. And the question is, if we set this thing up and let it go and let it drop a distance h, then what is the velocity? And I think you're supposed to, well, it's easy enough to find out what are the angular velocities of the two pieces, the pulley and the sphere. Okay, so what's a good way to proceed?
You could say that since there's no loss in kinetic energy, because there's no, or loss in energy, since there's no actual work done by dissipative forces, you could say that the final energy is equal to the initial energy, and that's pretty much just going to be the change in potential, or MGH is going to be equal to the final kinetic energy, since or the final potential energy is going to be zero, since it technically reaches height at zero, and then both things sort of are at rest, so there's going to be no potential energy from the beginning.
Good. So using the work-energy theorem, we just need to calculate the net work done, which is going to be by gravity. All of the tensions in the rope will do net zero work, right? There'll be positive work on one thing, negative work somewhere else. It'll all from the tensions. So the net work is the work done by gravity, which is just going to be the mass of the block times g times the distance that the block drops. God bless. And the initial kinetic energy is zero because it begins from rest. And then so it's just a matter of figuring out the kinetic energy for the whole system. So there are all these pieces that are moving in this different ways, and so we just need to figure those things out and relate them to each other. So there's the block has translational kinetic energy, the pulley has rotational kinetic energy, and the sphere has rotational kinetic energy. And there is a relationship between the velocity of the block and the angular velocity of the pulley, and between the velocity of the block and the angular velocity of the sphere. So how is the velocity of the block related to the angular velocity of the pulley?
V over R.
R omega.
Yeah, not V over R. V times, okay, yes. The angular velocity of the pulley is R times omega, or in other words, the sphere for the pulley, and this also equals RS omega S, right, which is the no slip condition. We assume that the rope is able to turn the pulley and turn the sphere without anything slipping. And having done that, then we can write down the angular velocities in terms of the velocity, and so the kinetic energy then is 1/2 times m plus I pulley over R pulley squared plus I sphere over R sphere squared times V squared. Okay, and then it's a relatively simple thing from there to get the velocity of the block. How about dimensional analysis? Does this have proper dimensions?
Yes, because the moment of inertia is mr squared and the
Good.
r's cancel out.
Moments of inertia are mass times length squared. The dimensionality of that is mass times length squared. And so each of these terms inside the parentheses must have dimensionality of mass, and they do. And so then you could check out something else. For example, suppose that both the pulley and the sphere have negligible moments of inertia. Then all the kinetic energy ends up in the translational motion of the mass. And so the final kinetic energy would just be 1/2 mv squared, right? So it makes sense. Okay. Now the yo-yo. Last one, number 4. Find the acceleration of the yo-yo. So my diagram there in the solution isn't quite what I had in mind. Of course, the diagram is. I told you, just consider that the yo-yo is just a cylinder with a rope, the string wrapped around it, like that. So the diagram is a little off. But you can do this in generality. You can still say that there is a radius around which the rope is wound around the cylinder, and also we can leave it general. We don't know that. We might say we don't know the moment of inertia of the yo-yo. It could be a hollow cylinder. It could be a solid cylinder, or maybe there's some other arrangement of the mass inside. Okay, so simple force diagram. There's just two forces acting on the yo-yo. How many degrees of freedom? That was not a word I've really used very much. How many ways in which this thing can change? It can change its height, and it can change its angle. It can rotate. So there are 2 degrees of freedom. There's a differential equation, which is the equivalent of Newton's equation for each degree of freedom. And then you have an acceleration. Since there's a no-slip condition, that gets you down to an acceleration and a tension. Are the 2 things you don't know, which you can then find. Any questions? Okay, so let me give you a problem to work. Let's consider this one. It's a little bit harder than what you've done so far. So consider a bowling ball. Let's take a surface that has, God bless, has some. First, let's consider an icy surface, no friction. And we just take a ball and we have it. Get it started sliding along the surface. What's going to happen to that? Say it again. What? They keep sliding, right? Let's look at this. So this is ice on ice. Let's diagram the forces acting on this. How many forces?
Got force grab, force normal, then you won't have no friction.
And that's it. So, is there a torque acting on the wheel?
Because of friction gives it its torque.
So therefore, it's not going to rotate. If it's not rotating to begin with, it won't start rotating. And if it's given an initial velocity in the horizontal direction, it will just maintain that. So it'll be uniform linear translation, and the thing doesn't spin. Okay, so, and if it were spinning, it would just maintain its rate of spinning, and it would be sliding still. So it's sliding, and so it is slipping, right? You don't have the no slip condition because it could be slipping. In fact, you could put backspin on this, right? You could put backspin on it while it's moving forward. It could be spinning backwards, and this just continues that motion. The rate of rotation doesn't change. The rate of translation doesn't change because there's nothing that torques the ball. Okay, so now let's take a little bit. This is the interesting problem. Let's suppose now we have a surface. We have sandpaper here. So we've got friction. Now we give it an initial velocity. And let's suppose for definiteness, let's call it a sphere. It's a solid sphere. But I would say in general, don't plug in the moment of inertia until you get to the end. You just use the moment of inertia in this problem, and don't generally start substituting a particular moment of inertia until you get to the end if you're given a particular geometry. All right, so what's going to happen to this? There's another force that's been added. What force is present now?
The friction.
And which way is that? What kind of friction and which way is it? Now remember, we're going to get it started without rolling to begin with. It's like if you could imagine, you kind of roll things with when you're doing bowling, so that's not a good thing. But suppose we get the thing sliding to begin with. It's initially sliding on the surface without spinning. So the initial condition is that it has an initial velocity, and omega is equal to 0 initially. Has an initial translational velocity and no spin. Okay, now what kind of friction do we have present?
Kinetic.
It's kinetic friction. Which way is it?
Opposing motion.
Left.
What's its magnitude?
Force normal.
U sub k
Times
UK times the normal force, which is mg. I should use the same m in both cases, right? Okay, so now we have three forces acting. Is there a torque produced on the ball now?
Is it on sandpaper?
Yes, sir. There's that kinetic friction is present, so that produces a torque.
Mm-hmm.
It'll start spinning up. Even though it initially has no spin, it's going to start spinning. So describe the motion while this is going on.
Slide and then it will start to roll.
Yeah, it's sliding. It's starting to roll faster. What's happening to the translational motion? It's slowing down,
initially.
and it's spinning up.
Until they're indirectly related.
Yeah, what's that direct relation?
There's no slip.
Until they finally reach the no slip condition. That is, the spinning increases, and the sliding slows down until they match that case of where there's the no slip condition. And then what kind of friction do you have? Static friction. Okay, so there's two kinds of motion here. There's two regimes. It will travel some distance, still slipping and spinning, but it will finally get to the point where its velocity equals r times omega, and then it will roll without slipping.
Will it still be slowing down or?
No, it doesn't slow down.
Are you asking?
Yeah.
Oh,
Is there a force present? What forces are present while it's rolling without slipping?
well, you still got the static friction.
What's the magnitude of the static friction? Mr. Flanagan.
Whatever it needs to be to keep it spinning.
Right. Yeah, and doesn't need anything to keep it spinning. No. So actually, the static friction will be 0 at that point when it's rolling without slipping. At that second part over here, the static friction, there is really no friction present. It's just rolling without slipping because it already has exactly what it needs in terms of its rolling motion in sync with its translation. So now there's actually no static friction present. I mean, the magnitude of static friction is 0 because it doesn't need anything to keep it from sliding.
Yes. If it's on sandpaper, it's going to stop. So yeah, slow it down. It's got to. If it's on sandpaper, it will stop.
Now it'll just keep rolling.
No, it won't. If you throw a bowling ball on sandpaper, it'll stop.
Not once it reaches. If you roll it without slipping, if you roll it at exactly the right speed to keep it translating, there's no dissipation.
Really?
Yeah.
So it'll keep on rolling.
Right. Yeah.
Wouldn't the air stop?
So
Well, you have air resistance and other things like that, but it won't be because it's not actually. There's no heat generated because it's not slipping on the sandpaper. As long as it's just rolling on top of the sandpaper, it doesn't actually. There's no friction present from the sandpaper.
Wait, so what was the condition that caused you to neglect or set static friction
We're
at
going to
0?
go back.
Because it's rolling at exactly the right. It's rolling at exactly the right rate so that there's no slip. So if there's no slip, there's no kinetic. There's no work done by friction. And so it won't slow down. It won't lose any kinetic energy. There's no dissipation. Okay, so let's consider this first section here. Where the thing is rolling and slipping at the same time. It's translating and spinning, but it's slipping while it does that. Because in that case, we would say that omega would be less than, omega would be less than R over V over R is what I meant to say, V over R. Right. R omega is less than V. It's not spinning fast enough. The initial value of omega is 0, and the initial velocity is VI. Now both of them are changing. The V is going to be coming up, and the omega is coming up, and the V is coming down until they match. There's no slip condition.
Are they independent of each other?
Yeah. How do we describe this? Okay.
With the rolling.
So we got the force diagram. What's the next thing that we need? Coordinate system. We need to describe how this thing moves. So we need what? How many coordinates to describe this kind of motion? 2. What should we use?
Whichever way it's translating is positive, and whichever way it's rolling is positive. Right?
All right. Let's call x to the right, and we would have
Clockwise. Yeah.
which way will it start to spin? It'll start to spin clockwise. Right. So theta will be that way. And the velocity is x dot, and omega is theta dot. Okay, so what are our equations of motion for those two? We have how many equations of motion? 2. We have one for each. So what's the equation for x?
You got the look at your two forces, so x double dot is equal to
negative sub k mg.
Acceleration is just minus mu kg, some fraction of g, which is determined by the coefficient of kinetic friction.
And since we'll say that the original x and original thing is 0, we just say
What kind of motion is this?
Original velocity
it isn't. Oh,
What
so
kind of motion is present before it gets to that point where it's rolling without slipping? While it's still slipping, what kind of motion is it in the translational?
uniform linear acceleration.
Yeah, it is. It's rather simple, isn't it? What's the velocity as a function of time?
Vi minus mu sub k gt.
Mm-hmm. Okay. The velocity is going down linearly with time. Okay, so that's it's very simple, and we could get the distance. The distance would be the initial position. Let's call it 0. VIT minus 1/2 mu k gt squared. So we know the time. We can tell how far it travels during that time. Now this is until it gets to that point where it's rolling without slipping, right? This does not happen after it rolls without slipping. Once it stops slipping, it's going to have uniform linear translation. It's going to stop decelerating. All right, how about the next part? What's the next equation of motion? We've got one, and we've even got a solution for it.
look at the rotation.
Yes, so what's the rotational equation of motion?
Theta theta double dot.
Now we need the torques. We need the torques.
Mu sub s.
And what are we considering to be the point of theta is, of course, determined by rotation around the center, right? So we need to compute the torque around that center. There. So there are 3 forces, so potentially 3 torques. How about the torque due to gravity?
0.
And it's not going to produce any torque. Why?
Because it's parallel with
Yeah, you can consider it to be acting on the center of mass. It's a symmetrical distribution. There's no net torque acting on this. How about the normal force?
0.
Why?
Same reason.
Yeah, and the normal force is pointed back up along the radius. So if you have a ball sitting on the table, unless the table is inclined or something, it's just going to sit there. It's not going to start spinning. Right? There's nothing that produces a torque. The normal force is just pushing straight up. It doesn't produce a torque. Okay, so the only torque that's present is the torque because of kinetic friction, and what is that torque in magnitude? In which direction? Almost mu k mg times r gives you the torque. And what's the direction of that torque? What's that?
Into the board.
Into the board, right. Let's point your fingers along the R. R is from here down. R across the force is into the board. So for that torque, there is R. And then Fk is back, and so they're perpendicular to each other. R cross F is just the product of the two. So it's R times R times mu k mg. So the angular acceleration is R is mu k m. Let me do it right this way. It's a little bit neater. M R over I times G. That's the angular acceleration. What kind of motion is this? Is that torque constant?
Yes.
As long as it hasn't reached that point where it's rolling without slipping, the torque is constant. So what kind of motion is this? Yeah, uniform angular acceleration. So this is ULA. I guess we'll call this UAA, uniform angular acceleration. Okay, so then what is omega as a function of time? Right. It's just the angular acceleration, which is a constant times time, right? The initial angular velocity is 0, so this is, we say that's 0, plus alpha, which is a constant, that thing. Okay, so now let's make a plot, and let's plot, what we're looking for is where r omega is equal to v, so let's look at r omega. R omega is mu k m r squared over I times gt. So let's plot v, which is coming down like this, v initial, as a function of time, and omega, which is coming up like this, spinning up. So this is vi minus what was it, mu k gt, and this is r omega. So I can plot them on the same scale because they're both speeds, both the same kind of speed. Mr squared I gt. It's increasing, and at some point they're going to match. And now it's met the condition, the no-slip condition, and from now on it will roll without slipping. It has achieved the no-slip condition. So we can find the time that it will take. How do we find the time it takes to reach that condition? Yeah, they're equal to each other. So vi minus mu k gt equals mu k mr squared over I gt. So in other words, we would have vi is equal to mu k g 1 plus mr squared over I t. That's when so this is when it reaches the no slip. So this is time to no slip. That's how long it takes it to get to the no slip condition. And we could see how far it travels by plugging in that time into the distance, which we have up here, x of t. We have that condition for x of t, so we can see how far it travels. So the distance it travels while it slips equal to put in the T no slip. Yeah. Now we should change that time. We should call it time of time. What the time that it's slipping. Total time of slipping. Okay. So we can find out how far it traveled. Kind of a cute problem, isn't it? I like it. Got some interesting physics, but notice that the motion is really rather simple. It's still uniform linear translation, uniform linear acceleration, actually deceleration, and uniform acceleration in the angular kind of motion until it gets to the point where now the friction actually goes to zero because it's no longer sliding, and then it's uniform linear translation and uniform rotation.
How is being
It's like giving it impetus. The friction, like instead of taking away, it's giving because it's making it roll.
Ah, so now we can see what's total kinetic energy that it has, right? So it's losing translational kinetic energy, but it's gaining rotational kinetic energy. But so is it going to have a total more? Is it going to be the same amount now? No. Why not?
Because kinetic friction is that long.
Kinetic friction has done work. In fact, we know the distance, and so we would say that the work done by kinetic friction is going to be mu k mg times that distance. That's the total work done by kinetic friction. So the total kinetic energy must have gone down by this much. So if at the end of the slip, we should have this much translational kinetic energy, and we should have this much, I'm sorry, not VI, and this much translational kinetic, rotational kinetic energy. And in fact, because it's not slipping at this point, then we would have this is when it is no longer slipping, not slipping. Okay, so that comparison of those two should be so the kinetic energy initially is going to be 1/2 mvi squared, and then we have the kinetic energy at the end, and we should find that the work-energy theorem holds. So some intrepid person would like to check us out here.
So what happens? What would be the kinetic energy if it is slipping?
So what happens to the kinetic energy if?
Like if it's still slipping, what would be the kinetic energy at a certain
Okay,
point?
so how is the kinetic energy changing in time? Does anybody remember? There's a relationship. If there's a force, net force acting on a body, the kinetic energy is increasing or decreasing.
In this case, it's decreasing.
Yeah, so it's decreasing. So let's remember this. Okay, so we did it before with translation. And now we would have to extend it to rotation. So that would take a minute for us to do. It's in there. It's in the book. But let's recall for rotation. The case for rotation, if the kinetic energy is 1/2 mv squared, then let's look at the derivative of the derivative of the kinetic energy with respect to time. mv times v dot, and ma is the force, so it's fv. Or in terms of vectors, if k is 1/2 m v dot v, then k dot is going to be m v dot a, and ma is the force, so this is f dot v in more general result. So that's the rate of increase or decrease of the kinetic energy. If the velocity is in the direction of f, that is, if f is in the direction of the motion, what happens to the kinetic energy?
Increases.
It's increasing. F dot v is a positive. If f and v are in the same direction, it's increasing kinetic energy. But in this case, the friction opposes the motion exactly backwards from the motion. F dot v is a negative. So the kinetic energy is decreasing. But F dot V, as long as it's in that phase of motion where it's slipping, then the force of kinetic friction is a constant, but the velocity is decreasing. Right? So the rate of decrease of the kinetic energy is less. It's slowing down its loss of kinetic energy because the velocity is decreasing linearly with time. So as it goes there, it starts off losing some kinetic energy, and then as it slows down, it's losing less kinetic energy. Okay, and then when it hits that no slip condition, then it stops losing kinetic energy altogether. Okay, so that would be an interesting exercise. Somebody check out what we've done here. You're looking for some extra credit. Work through this problem. I've got you most of it here. Figure out what happens to the change in kinetic energy. Does the Work-Energy Theorem actually work in this case? And it should. If we've done everything correctly. It should match up that the kinetic energy at the end is equal, the change in kinetic energy is equal to the work done by friction. It will be negative mu k. There's a negative here. You didn't catch me. Work done by kinetic friction is negative because it opposes the motion. Okay. Kind of an interesting problem. I like this one. You could ask the question, if this is a hollow sphere or a solid sphere, will it take more or less time for it to reach that no-slip condition? Does one lose more kinetic energy than the other one? Be a simple thing to ask. So how does the distance vary? The distance, there's the time. So the time for it to reach the time at which it will keep slipping, if I increases, then the time goes which way? Yeah, the time. If I increases, the time also has to increase for the same initial velocity. It takes longer for it to spin up. That makes sense. It's got a greater moment of inertia. It's going to take longer for it to spin up to meet the condition of no slip. So that makes sense. The bigger the moment of inertia. So a hollow sphere and a solid sphere, both with the same mass, same radius, but different distribution of the mass inside. Hollow sphere will take longer, will roll farther, lose more kinetic energy total. Right? It's a nice little problem. It's got a lot of interesting aspects to it. Okay, so for the homework for Wednesday, I want you to take this test. And I want you to try it like it were a test. The test on Friday will be similar in that it will exercise, test your knowledge of the same principles. But it won't. It's up to me to try to come up with something that's different enough, because I don't want you just regurgitating memorized stuff. So there are two problems on here, both involving stuff from Chapter 7. So I want you to take the test. Take it like a test. Find some time. Give yourself about an hour. And take it like a test. See how you do. Grade yourself. I'm not going to give you a solution yet. And then keep working on it after that. If you like, that's fine. But try to perfect your answer. In other words. Yes, sir.
Which moments of inertia will we need to know for the test? Just all the ones in the book?
Oh, yes. So if I give you something where you need to know the moment of inertia, I'll give you that table from the book.
Okay.
All right, thank you.
Yeah. So you can refer to that table if you feel like you need to know the moment of inertia in one of these problems. Just look it up in the table. I don't expect you to memorize moments of inertia, except the parallel axis theorem. You should know how to do that. I think that's in the table actually, but you should understand it. Remember that. Any other questions?
So the thing about two-part test is.
Yeah. So it's just going to be one part. I've shrunk the test down to just chapter 7. It's going to focus only on this part, chapter 7. So you should know how to. That table at the end of chapter 7 where he parallels the kinds of motion like let's see, yeah, what page is that, Mr. Creer? 339. On page 339, there is a coordinate for translation, a coordinate for rotation, a velocity for translation, a velocity for rotation, and acceleration, linear acceleration, angular acceleration. Something like a momentum for a rotation is the angular momentum. So there's a moment of inertia corresponds to mass for the two different cases. Kinetic energy. How about an equation of motion would involve force is the derivative of momentum with respect to time. And here we have torque is the derivative of angular momentum with respect to time. And so forth. Right? You should have all of that. So you should be able, just like when we were doing the problems with the sliding, you should know how to write down the equations of motion and identify the cases that are just uniform linear translation, uniform linear acceleration, be able to write down the solution for those and solve for things like how long does something go until it hits the ground or something. Then in the same way, you should be able to then in uniform translation, you should also be able to apply the work-energy theorem involving friction and other things, and gravity. And in a similar vein, the rotational, you should be able to write down equations of motion for rotational motion, be able to solve them for the simple cases of just uniform rotation and uniform angular acceleration, and apply the work-energy theorem for cases of rotational motion, where you have combinations like these Atwood machines with rotating parts and other things like that. No slip condition, parallel axis theorem, be able to write down a kinetic energy for something which is rolling without slipping. There's two different ways to do it. You should be confident that you know which, do it one way and get it right. You should be able to get it right two different ways, but you should at least be able to get it right one way.
Should we expect it to out like this?
Yeah. Any questions? Let's look at APOD. That was in the southern hemisphere. This is not ISON. This was a comet from a couple of years ago, but it was only visible in the southern hemisphere. So we didn't get to see what was.
Can we just call ourselves the southern hemisphere so we can see it?
We didn't get to see it. So this is 2007, 5 years ago. Comet McNaught. That's a pretty comet, isn't it? That would be spectacular to see. So if you haven't seen a comet before, you can't detect any motion. It just looks like that in the sky.
That was like if you're on the equator and you couldn't see it. You just have to equate.
That's really spectacular. Okay. And let's see. The other one here is this is an interesting picture of an aurora with a funny-looking cloud here. Pretty cool. All right, so I'm going to let you go early today.
Early?
2 minutes early. I know it's a shock.
Don't ever.
Yes.
That we will ever say that.
Regular office hours on Friday, which means before the tests.
What time is that? Is it during class?
Here in class, right here.
It's going to be 2 questions.
I expect so. Yeah, that's my goal.
Yeah. And I was like, what? No, they want to drop this test. So they was like, yeah, the yo-yo test. I'm like, okay. It's a yo-yo test. We were to start to look back.
When you said there were
What that rotation
different
do,
ways.
Hold on just a second.
I like your shirt.
Okay.
When you said there was two different ways for finding the kinetic energy. It was
Right.
the
So-
second one using the parallel axis theory.
Right.
That was, and then using it revolving around the point.
Right.
And so it's basically just revolving around that point for a certain distance. is
Yeah,
what that-
and that works only for if it's not slipping, right?
Mhm.
No slip condition.
Okay.
So if it's slipping while it spins and translates, then you can't consider that it's rotating around a point of
Yeah.
contact because it's slipping. So,
Yeah.
so you need to go back to the other way of doing it then.
Which was just the translation plus the rotation.
Right.
Okay.
Right.
So if you do the change in kinetic energy equals the work, and then you find that, can you use the conservation of momentum to prove it that they're after that?
Say it again.
So if you're setting,
Talking about the rolling problem?
yes, you wanted it proven.
Yes.
So if you were to,
Well, let's see. This isn't true though, right?
No,
Because
no,
the
that was-
difference-
I did it
yeah,
down here.
This would be if there were no work by kinetic friction, right? So this would be this plus, I'm sorry, minus the kinetic friction, minus mu k mg d, right here.
I think I did that down here. I think
Okay.
I realized that.
All right, fine.
Maybe?
Okay. Yeah.
Does that look about right? Okay.
Yes, right. Yep. Yes, it does. And yes.
So-
Okay. This looks good.
So then I just thought, if I solved for the
That's right.
initial and final
There you go.
velocities, and then I could just use conservation of momentum.
That's right.
Is that,
I think, let's see now, what we've got, so you've got a distance here though. Oh, wait, say that last part again.
well, I thought
Conservation of
if I just solved for the final velocity and the initial velocity, and then use conservation of momentum to try and prove, like, the initial is going to equal the final, but I don't feel like that's gonna work, because the mass is the same, so I'm not real sure.
And you've got a distance in here.
Right. I'm just kinda stuck on where I'm gonna prove it.
Yeah, I think you need to find, really what you need is
The distance?
that distance and that velocity. So really what you're trying to show is that the velocity, which I derived there for when it, so the velocity that it has when it reaches that no slip and the distance it takes to get there, that those, which you get from
Right.
solving what I had, actually satisfy this
Okay.
as well. That's
That
what-
would- that-
that's the easiest way to do it, I think.
Thank you.
Okay, you're welcome. See you.